Thank you to the Serverless Days NZ coordinators, and thank you very much for having me. My name is Dixon. I'm a principal engineer at Versant here in Australia, and I'd like to talk to you today about code reuse and serverless APIs, and in particular, a core piece for me. I love writing serverless pieces of code as well as event-driven models in the AWS ecosystem, and in particular, one of the things that I really like doing is how we basically build serverless APIs in AWS. Now, when we're building serverless APIs in AWS, we have a number of options. So typically our orchestration will look at the idea that we have CloudFront, then an API gateway, and then we have a number of ways in which we can orchestrate this. Not only can we go and talk directly from CloudFront from an API gateway into an AWS service, we can do a Lambda integration as an AWS proxy call. We can go back to a HTTP integration, so we can call back to any of our other APIs or existing HTTP endpoints. We can do a VPC link. We could even return a mock response. So if we had an endpoint that we just wanted to return a static context from, we can do that as well. But we have a number of options about how we want to do serverless APIs in that space. So where do we want to control the routing? So we can have everything flow back to a single Lambda, or we can have one Lambda to basically per endpoint as a context as well. Probably common questions we have is how we handle stateful data storage, as well as what we bundle with the API, whether we're using API gateway late stages or whether we're using an independent gateway per environment, whether we're synchronous or asynchronous in our call sets. And as you can imagine, this becomes quite complex when we talk about some of those options that are available. Let's break down our example. So first off, we're building a RESTful API. We're using AWS SAM to do our build, deploy, and packaging. Thus, the example will be CloudFormation based. We've built the example in Python 3 in a mono repo, and the demo is going to talk to S3 and Dynamo for its stateful data. We're of course using the git char as a simple version of semantic versioning within the environment. Now, as an example serverless API demo, we've got an API gateway backed by an ACM certificate, and that gateway has 4 paths of which are backed by individual lambdas. We have a create PDF, a list PDF, a get PDF, and delete PDF. Now, each Lambda will basically be logging through CloudWatch logs and implementing X-Ray to give us observability and telemetry within the example. We of course have Dynamo, DB, and S3 for stateful data. Even with an example serverless API, we still end up with one of the core software development lifecycle problem spaces that exist in this ecosystem. And at its core, it's how we deal with the common code base between the Lambda functions. In particular, given that we have the 4 Lambda functions for the 4 paths, we know that we're interacting with common libraries such as Boto, as well as the generating a response as being part of a RESTful API. So as such, how we deal with that common code base in our functions really leads us into whether we're duplicating through dependencies or through committed code. As such, this determines some of our interactions with our libraries and our dependencies in terms of how we approach that solution, which has impacts on our Lambda function size and potentially the number of lines of code that we have to write and manage inside our Lambda functions. Let's explore this a little bit further. As a request comes into our API gateway and it funnels into the create PDF function, that function is basically going to generate a PDF for us. It's going to put that payload through the Boto SDK into DynamoDB. It's also going to write the binary into S3, and then it needs to respond back to the originating request as a JSON payload for the RESTful response. How we do that is we'll basically interact with the Boto SDK, we'll interact with custom code that we've written around the generating of the PDF, and of course there's the way in which we do the response object back to the API gateway. A solution to this is utilizing Lambda Layers. So at their core, a Lambda layer is an independent deployable code base, dataset, or structures. It drives a consistent interface and interaction with our code and our libraries. A function can reference up to 5 layers. A Lambda layer gives us a separation between our business logic and how we interact with systems and services inside our ecosystem. Through this, we're able to leverage and present Lambda layers not only across account, but across our wider AWS system and even present them publicly. When we do reference multiple Lambda layers, they will get rolled up into the opt directory, and dependent on our language, It'll be in a specific path. For Python, that path is /Python. So let's look at the code base differences between a function that is utilizing a Lambda layer and a function that is not. So on the left hand side, we've got a function here where we're basically not utilizing a Lambda layer. As a result, we're having to import all of our core libraries into the actual discrete Lambda itself. We then, of course, got to actually reference and write all of our functions, exceptions, and all of the classes associated with generating the PDF, talking with the Botto framework, and building our response for the RESTful response all have to reside in that function. And as you can see here, we end up with roughly around 257 lines of code to roughly perform all these discrete functions. Whereas the Lambda function on the right-hand side, we can see specifically that we've got a dramatic reduction in the number of lines of code. And in particular, we're just having to handle the initialization and build the response. We're roughly importing all the other packages, and we're doing so through the Lambda function. So as a total size of the Lambda function and the total code, we've actually dramatically reduced the size, not only the number of lines of code, but we've also reduced the size. Effectively, the way that this works is that because we're now importing the Lambda function, we're not having to build the Lambda with all the packages inside of it. We simply reference them as part of the layer and the presentation they're in, subsequently reducing that duplication layer. Let's take a moment to talk about Python inheritance and use a classic example to sort of run through that. So let's talk through the idea that we wanted to represent shape in a Python class. We'd probably be really keen to understand the size of the shape. So effectively, we're going to probably just set it to 0 initially. We probably want to just have some dunder functions just from a Pythonic context, so refl and stir. But we're probably really focused on the perimeter and area of the shape as being key functions that we want to get information out of how we would do that for each shape. The problem is we won't know how to calculate the perimeter and area until we understand more about the type of shape, or depending on the shape type. So let's talk about the idea that we want to implement this further. So we then had a parallelogram that was inheriting the base class shape. Now, as a four-sided shape, we know that we have a width and height, and we're going to add them as members to that class. And effectively, we're going to throw the sides at the super function to initialize the base shape class. Now, with the parallelogram, we know that we use the width times 2 plus the height times 2 will give us the perimeter, and that the area is calculated as simply the width times the height. Now, we know there's a special type of parallelogram, which is a square. Now, as a square, its perimeter and its area are still calculated the same way, but probably what differs is that we only need a single side of a square as an input to define a square. So with this, square is inheriting from parallelogram, and we're basically initializing it with a side, and a default size equals 4. We set that as a member to the class, but when we initialize it, we're initializing not against shape, but against parallelogram. And in that context, we simply throw side twice at the parallelogram's initialization function to set the width and height. And subsequently, we could call the perimeter and the area functions for square, knowing that we'll get the correct calculations back. So because they don't differ, and because we've initialized the parallelogram class correctly, we know that we'll get the perimeter and area class back. And this is a core example about how we can use inheritance to override certain functions and ensure that they're correct where we need to. But if we don't need to override them, or we don't need to change them, we can simply use the ones we've inherited from the inherited class. So let's now take a look at how we could use that in a practical sense in terms of how we would interact with the Botto 3 SDK for AWS, as well as looking at how we would calculate headers as a RESTful API back to our client response. Okay, let's have a look now at the actual mono repo and have a look at some of the code and how we implemented it, in particular with the Lambda layer. And then we're going to look at the functions that are then importing the Lambda layer and how we're basically referencing some of that code base and how we leverage it in a more practical context rather than just simply the shape example that we gave or looked at earlier. First off, in terms of the actual Lambda layers, we're going to look at some of the core pieces about how we interact with DynamoDB as well as S3. So at its core, we start with the DynamoDB. Here in the initialization of the DynamoDB class, we're taking a parameter called table name, and then effectively we're creating a resource bound to the table. And then we effectively have 4 functions within there. So we have the delete, get, put, and scan for the DynamoDB table. And in essence, we perform a similar function when we look at the S3 one. We effectively have the client and the resource. And we effectively have four main functions: create multipart upload, delete object, get object, and put object. Now, where this differs, or where we take another step on it in terms of introducing some of the business logic or custom code, is how we want to write some of the more friendly interactions, and in particular how we want to handle certain flows, such as when exceptions are raised, and how we want to handle our logging and interaction, and some of the consistency we want to have around those interactions. So here we are setting up our own logging space, but we're also talking about how we handle try, exception, and else logic blocks, and how we handle an exception when it does get raised, and what we're logging and how we present that data back to, in this case, CloudWatch logs. Now, where this becomes more interesting, outside of just simply wrapping around the Botto SDK for AWS, we then actually go into more of the custom code that we've written, which in particular is really around how we interact as a RESTful endpoint, how we handle the response and return response object that we send back to clients. So we have our payload, but one of the core elements is how we handle all the headers that we need to generate, from content length, content type, the date, as well as the actual cause headers if we have any, and effectively what the cache control would be to ensure that data is or isn't cached depending on what our use case is. Here you can see we basically initialize the endpoint, but in particular we have a build headers function. We have all the various helper styles, so how we're generating content length, how we're generating an e tag, the date. In particular, how we handle the build response, so when the response is in a successful state or when it's in error. And in particular, how we're handling validations of requests, headers, and response objects. Let's have a look at how we actually implement this or call it from the create PDF function. So create PDF is of course sitting off the API in the create PDF. As a post request, we're of course getting data into this function. So we're receiving data from clients or from a web form or otherwise. Now at the start of this, down the bottom here, we can see that from the Lambda handler, we are basically creating a PDF object. We're of course taking in the event and the context object, and we're passing them into the actual class itself. And after initialization, we're calling the response function associated with the class. Now at the top of the class, in the first few lines, we're actually setting up the logging context for it, so how we actually interact and log things into CloudWatch logs. We're of course taking the event and the context object, and we're setting them as member functions within it. We're also passing them into the super function. So we need to call the super function to initialize the base class. In this case, the base class is endpoint. So class create PDF is inheriting class endpoint from the Lambda layer. We then of course have three parameters that we're taking in from OS environment. And these are parameters that we're passing through CloudFormation during the creation of the Lambda function. So in particular, we're taking in the import values of our bucket, our KMS, and the table that we created earlier through the CloudFormation for the S3 bucket, as well as for the DynamoDB environment. We of course then set up some standard business logic pieces that we have. So the endpoint that we expect for validation, the status, and effectively the response payload we nullify. And of course, we take in the body object or key from the event dictionary, and this is effectively the payload of data that we received from the client. Now, as I mentioned earlier, once we actually initialize the class, we do call the response object, in which we effectively go through a try, except, else, and final block, in which we're basically generating, going through our custom flow. So this is where we have the glue of what the function is doing for us in this case. So first off, we call a create PDF function. And again, we're calling create PDF from the Lambda layer. So it's code that exists outside of this call function. We're submitting the data into it, and we're effectively calling the build PDF, which returns a byte string for us from the fPDF class that we're using there. We generate a dot key, which is effectively just a random UUID. And we're going to use that dot key as the document ID and the unique key for both not only the item in the DynamoDB table, but as the file name inside the S3 bucket. And of course, we write to the S3 bucket through the S3 tasks write file function, in which we pass through the PDF as a byte string and the dot key. And then we have the DynamoDB tasks, in which we're basically writing the item. So we're sending in the key as the dot key and the payload as the data load itself as a JSON dictionary in this case. Now, assuming along the lines we didn't receive an exception in the form of a value error or an attribute error, or any of our custom exceptions that were raised where we had an issue with, say, the Botto SDK talking to Dynamo or to S3, or a general exception, we will basically go into the else block, in which we basically have a success. We implement the document ID into a custom dictionary and the message of success. Now, irrespective of whether we did raise an exception or not, we will always generate the status or set the status and effectively set the response payload, because we will use those when we go and call the build response package. So in that context, this is where we're going back and calling build response as part of the endpoint class. So if we jump back into that, that is effectively where we, within the build response, we are taking in the status code, we're evaluating that whether the total response is of a success or a failure, and we're building out the correct object to pass back to the API gateway. So as a AWS proxy, this is the payload that we need to send back. So we have the status code. On a success, we have the status code, the headers, and the body. And again, because we're using an application JSON response type, we're just simply JSON dumping that payload back into the actual client. If it was an error, we're of course setting the status code, the payload or the error message attached to it, and subsequently the request ID to match back so Lambda can actually align those pieces back. We of course call the function, so within the headers we will call all of our helper functions to generate that headers consistently, and through this way we're able to gain a consistent approach for all the Lambdas in terms of how they will implement the baseline classes and send back a more practical way of using Lambda layers. This way we don't have to embed the code in each function. We can have the code in the Lambda layer itself, and we simply bind the Lambda layer in and provide it as an object inside, the file system that we can then subsequently import into the environment. And thus, we have a practical example about how we can utilize consistent approaches around using certain third-party libraries in the form of Boto, but also how we can use even our own custom code to provide a consistent library and approach to how we interact with, and in particular in this case, respond as a RESTful response back to our clients. All right, time for the demo time. Now, thankfully, this is a recording, so we don't have to pray too much to the demo gods. But one of the things we are going to do is we're going to step through the interactions with the API, look at how we're getting those back, and just step through the demonstration. But again, the demonstration is not here what we're trying to prove. Really what we want to do is go into and validate. We're seeing the assets, we're seeing the interactions, but in particular, go through the Lambda code base and see that we're getting the interactions that we should be, and the connection to the actual Lambda layer itself. So we're going to just step through some pre-curls. So again, here we have a curl that's basically going off to hit the create PDF function. Now, effectively, this is a JSON payload. Its key value is table data, and it has an array of arrays in which it's basically just got some standard data: first name, last name, email, and a fictitious zip code. Now, all these people are fictitious. There's no PII here, but effectively on that request, when we kick it up, we will get a doc ID back and a message of success. Now, if we go and hit the list PDF, we'll subsequently see that we've got that document sitting inside DynamoDB off a scan result. Now, if we go and create a few more, now the payload is completely decoupled. We're generating a random hash for the document ID. Again, you may do this differently in your application. You may want to use a variable or an ID or generated off a piece of data set that was given to you. But indeed, we can see now that we can see the other two documents now do exist in the DynamoDB space as well. Now, one of the core elements that we can do with this is, of course, we can go and delete a actual document that's basically being pushed into the environment. So here we can see that D3AF is no longer available. And effectively, if we go and basically kill the list PDF. So we can see that we're interacting with it. We can create documents inside the DynamoDB environment. We can delete them. And subsequently, we have those spaces. Now, one of the core elements is if we actually jump into the environment and into the AWS environment, we can actually begin to see what we're actually seeing happen inside this environment space. So if we jump into the S3 console, we refresh the page, we can now see we have those two documents as we expected them to be. Here you can now see we can basically go and download the object. and effectively open it up. And we can see there the fantastic serverless data hero, the magical unicorn, the lovely, lovely rainbow, but more importantly, you can see the table data that we have there. And that's an example of how we can basically save that data set into that space. So checking the file out of S3, and in particular, if we go into Dynamo, into our table spans, into PDF table, we can subsequently see the 2 items there associated with what we're seeing, as well as the subsequent payload of the table set within that space. So we can see that we've functionally got these APIs from a create, a list, and a delete. We can see that we can interact specifically with those 2 services. And that covers roughly that demonstration element of how we're seeing that function go into that space. Let's take a moment to talk about the key takeaways from this talk. Lambda layers are a fantastic way for us to reduce our code duplication and also drive reuse of common interfaces and common libraries in our environment. It's a fantastic alternative to packaging our code up, pushing it into a repo, and subsequently pulling it down as a dependency. We can use it to not only handle inheritance, but also dependencies and libraries. Of course, Lambda layers are supported across all the languages supported through AWS Lambda. Again, we can have Lambda layers not only support our code, but also be available for our datasets, objects, and of course, runtimes. And we are able to present it to our entire AWS environment, showing it across accounts, and even possibly presenting it publicly. For anyone interested in further learning on the topic, Chris Munns, a principal developer advocate within the serverless team at AWS, has a fantastic talk into Lambda layers and the Lambda runtime. In it, he goes through his own example and talks through the way in which you're able to execute a Lambda runtime. The YouTube link below will take you through to that talk. And with that, I'd like to conclude my talk, and thank you so much for joining me today. You can find the code base and the example in the GitHub location in the slide above. And again, thank you for joining me. Enjoy the rest of the conference.